Okay, welcome everyone. This is last collective meeting for green projects, and next week, according to our schedule, we are completing course. Previously, I mentioned that maybe we can give more tasks, etc. But currently, we have intention to complete everything like according to schedule. And also, we are thinking there will be certificate telling that we are passed the course. And maybe we can also have some certificate. They follow all these presentations, but maybe didn't make enough progress reports. Maybe we can prepare some certificate for attendance kind of participation. It will not say you passed or you failed the course, but it will say you just participate this course. Because otherwise it would be failed. So we find some such a solution. So instead of giving more time, we really want to complete it, almost everything in these 2 weeks. And then you will have this writing period, 4 pages, up to 4 pages articles you should write. We will make announcements about it probably next week. And presentations will be exactly this week of 23 of January, but we will also announce the exact dates. It will be public event, and 1 week before, we will ask you to make presentation within your group. So basically, you need to prepare, let's say, the first draft of presentations around January 15. You should make a kind of demo within the group to your mentor. Maybe you can get some feedback, etc., and then you will be more ready for this public event. So these are some updates, and we will share more in written form in the Slack. Today I will start from the 21. Bill, are you ready? Or who will present? I will allow every participants can share.
Yes, I have the presentation ready. Let me go ahead and share it. Give me 1 second.
Bill, your group should do another presentation next week, okay?
Okay, sounds good.
This
Yeah, we have some items lined up, so we should be able to come up with some presentation. Okay, let me share my screen. Hold on 1 second.
Because we missed one presentation, and you should complete it one more just next week with Blue projects.
Yes, that's correct. We did miss one. So let me share. Let me know if you see the screen.
And tell me who contributed to this presentation.
For this one, Wally and myself,
Okay.
we had a meeting a few days ago just also to discuss, actually over the weekend.
Okay, and Tuba didn't contribute, correct?
Not since the last presentation. So I'm not too sure if she's here. If she maybe
No, I don't see her. I remember she didn't contribute last one, and also she didn't contribute this one.
Yeah.
Okay. Okay, thanks. You have 10 minutes.
Okay, do you see my screen?
Yes, yes. Please
Okay,
continue.
so yeah, so this is a report for this week. So what we were able to do over since the last presentation is we were able to sort of reach the limitation in regards to what the primary task is, which is the integration of MIDIC methods with Classic. And so what we did is we were able to complete 2 what we call executors, which are basically methods for executing circuits against an external system. In examples on the MIDIC site, it's usually done against IBM or Circ or Penny Lane executors. We created two related to Classic using two methods that were described by our advisor. One uses the API wrapper, which these are all done using the SDK. The API wrapper is not well documented, as was mentioned, but we were able to at least get some work done on it and create an executor or executor using async IO for asynchronous calls. And then we were able to use the classic model object in the SDK to create a method to execute circuits against. So the first one is called the API wrapper. Because it's not heavily documented, we had to update the execution preferences. We were able to figure out how we could get execution preferences pushed to the executor, and essentially the only type of noise model or noise type that we could introduce through the classic system was bit flip probability. So we went ahead and used that. Because again, we didn't have a lot of documentation on this method, we were able to take a serialized program, convert it to JSON, modify the settings of it by hand, essentially modifying different pieces of it, and then converting it back to a serialized program and then running it against Classic, using the Classic SDK. The second method was a little easier to use. On this first method, we couldn't complete the last part of it because currently, if you see there's we're using MIDIC's ZNE.execute with ZNE, where you can pass a circuit and an executor or an executor. But because we were using the API wrapper using async IO, we were not able to get a good result from this because the ZNE execute with ZNE from MIDIC does not allow you to pass an executor that requires a wait or an async. So that didn't turn out to be something we could technically use. The second method actually uses the Classic model. And so we were able to utilize that. We created a model using a define function. This is all documented within the Classic's site. We created a very simple circuit. We were able to create noise properties and then set those inside execution preferences. So we set the number of shots and the noise preference. Again, we're just playing around with this number here, which is the bit flip probability. And we're able to run this one and get mitigated and unmitigated results. So that turned out to be the better way to actually execute against Classic, or at least integrate with Classic. And so some of the things that we did once we ran these two different methods, we basically just compared what the original IBM executor was doing. And again, we ran just a few tests, nothing too exciting, but the IBM executor is using depolarizing as a noise type. We have some just, different results there. And these change depending on how many times you run, how many shots, etc. But this is just giving you a general idea. Against Classic, we were using bit flip force probability. And so you see some unmitigated results. As we ramped up the bit flip probability, you get a lower result here. And then, of course, you get pretty good mitigation results. And then if you want to know more about error, the types of error, between these two here, you can go to this site, and there's an explanation of all the different types of errors that are introduced on the quantum side. So these were all run against simulators, those results, the Chasm simulator. We made an attempt to run against IBM's real hardware, but IBM recently changed their pricing model. And just to give you an example there, the free plans that most of us were on now only give you access to their 127 qubit systems, which are based on the Eagle processor. You have to actually upgrade through the IBM cloud to actually get access to some of their smaller systems. In the old days, we were able to get access to all the systems that were 5 qubits, 8 qubits, 10 qubits, etc. and now you can't, you have to upgrade. And what was happening is, as we were trying to run our experiments, we were getting queue times of up to 2 hours. Even though there was only 30 or so jobs queued on these systems, I believe there's 3 Eagle processors, the wait times were excruciating. So you'll see some there, like for example, there's a 2-hour wait on IBM Osaka. And then even though the actual program would only take a few seconds, we had to wait. So this became, you know, a hindrance for us to actually use against real hardware. Now, we may try fake hardware in the next few weeks, and then possibly do use some real hardware. So what do we have upcoming now, since we've sort of reached the limit? Is we have a couple of paths forward. One is to compare MIDIC's error mitigation against Qiskit's error mitigation, because they do have 2. They have ZNE and PCE. I'm sorry, PEC. And a second item we might try is try MIDIC against some circuits from Classique's examples. And then possibly some examples from some of our past projects. A few of us have some past projects we worked on. And then try to determine if there's a limit on the MIDIC side related to circuit depth or complexity or circuit size, and see if we can see if there's a limit where MIDIC breaks. When we first tried to run a few of the Classique circuits against MIDIC, some of them failed, you know, with some errors. We're not too sure why, but we want to see if maybe that it was related to the type of circuit that we were running, etc. I'm pretty sure we're probably going to end up doing these 2, not so much this one. We only have, you know, a limited set of time. So by and large, we're probably going to try this second one here to run MIDIC's error mitigation against some pre-existing circuits that we had already generated. Now, this comes out of Classique's scope or realm. At this point, we're probably just going to be doing some error mitigation techniques. And just to give you an example on some of the circuits that we've run in the past, these are the results from a image representation task, a project that I had worked on QWorld, an earlier project. And you sort of see here, these are the ideal results from a simulator, and these are results from a fake computer, or a fake quantum computer, which is a simulator that's modeled after a real computer, quantum computer. And you'll see the results are really bad. So we were hoping to maybe take it in the next few weeks to try to see if we could get better results from a fake quantum computer, something closer to a simulator. And that's all I have for this project.
Okay, thank you, Bill. So you can still make some progress and present next week. And of course, when writing paper, you can still do more and include in the paper also. You don't need to.
Yeah, and Wally and I have actually started writing a paper just on ZNE. We're going to try to concentrate on just one method, which is ZNE versus PDD or PEC. And then we'll add some of these results to.
Okay. So during writing, you can still do some experiment and just make.
Yeah, definitely. Now I think we get to the point where we have our methods built and we can start experimenting. And we do have all this published, so we can, you know, we can utilize it as necessary and continue with experiments.
Okay. Okay. Thank you. Any question or comment? Eden?
Yeah. So thank you, Bill. So a few questions. So one, the high level flow of what you're doing is you're creating a model with Classique, then exporting to QASM, and then from the QASM you export to MITIG, apply some error mitigation, let's say the ZNE, import back to Classique, and then you can send for execution from there. Is that correct?
Yes, we're using strictly the Classique Python SDK. But yeah, we do convert it over to QASM at some point. We start off with Qiskit circuits, and then we reduce that to QASM, and then we feed them into either the IBM executor or the Classique executor. But yeah, we do come down to actual QASM. We did have to remove the measurement portion because I think Classic or the MIDIC, it was MIDIC who had an issue with including classical and qubit registers. So we had to strip that part out of the circuits that we created. But yes, what you described is essentially what we are doing.
Okay, so cool. So as I see it, the advantage of a Classic, you can get them in two ways. So one is to create models and to create new algorithms, and second is to have access to basically every hardware provider, and to execute also offline. So first, I suggest that you can start the flow not from a Qiskit code, but from Classic code, and then to export as QASM, and then to send the same QASM to MITIC, and then the flow continues as you did until now. And secondly,
yeah, I'll stop you there. That's a good point. We did actually do some experiments where we started off on the Classic side with some of the boot camp circuits. We took them to QASM, but I think that some of the ones we created initially were a little more complex. And so we tried to run them through MIDIC, and we saw some errors. Now that just may be because we didn't take our time to do it correctly, but I can follow that. We can make that attempt to grab from Classic something that we synthesize or create in Classic and then pull out as QASM.
Okay, cool. I think this will be a nice work. And then secondly, I understand that the waiting times, thank you for letting us know that we can only run on the IBM hardware on the 127 qubit machines. But why is it a hindrance for you that there is a queue of 2 hours? So with Classic, you can just send the job, and then you can also log off and come back the day after, and then you receive the job in your IDE. So why is it an issue for you?
Oh, well, currently when we run we were trying to strictly use the Classic SDK. When we run against on the Classic side, the job ID or the execution ID that we get, we do not, it does not show up on the interface, was one thing we were asking about, I think, in the support. But that's a good point. We can try to see, but I think it's because on the MIDIC side, whenever you execute there, for example, ZNE, it will throw an error and will say does not accept the async IO. Now, we didn't try it with the model. No, we did try it with the model and that worked, but we didn't try it against real hardware. I can see, we can find out if that's possible. I mean, I think that might be something that we can try, just let it go and then wait, to come back and get some results. And then I know we can call up the results from a job that we execute as long as we save the job ID that Classic provides. So maybe that's something we can try.
Yeah, so I would start as a first step, just like at the end you receive back from MITIC, you receive a QASM. So I would upload the QASM to the IDE and then just send the execution over there to the IBM machine. And then you will have the job ready for you when you come back. So you don't need to wait or to save anything. So just as a first step. And then you can do what you said with the retrieving the job ID from Python. So this is the first thing I suggest you can do. Secondly, you can have access to further machines via Azure Quantum and AWS. So I think they give credit for free, and you can use them from the Classic execution.
Yes, yeah, and those are some things that I've worked on the outside, but not going through Classic. On Classic side, because I'm more familiar with the IBM side, I tend to stick to the IBM processors. But yes, I think those are great suggestions.
Cool. Thank you.
Thank you.
Okay, thanks, Eden. It's pity that we didn't have you like at the beginning time. 26 educators.
So now
Alvaro,
it is the group unified group. We have a unified group now.
Yes.
Now it's
this will be your last presentation.
Educators Minds. We joined the names.
Yes, I remember.
Okay.
This will be your last presentation, and you can start these 4 pages also. All these 4 students are contributing to presentation, Alvaro.
Let me see the history in the Okay, I am sharing the screen, okay?
Yes.
Let me see here. We have the history of the changes. Rishi has, bueno, myself, Álvaro Gómez, Asu Vila, and Rishi again, Álvaro again, and let me see, Manjula, really the November 28th is the last
Okay.
inclusion. Okay.
Because I was especially curious about him. Some of his individual reports are also missing. So
Okay.
basically, he didn't join to today's presentation. Okay, you have 10 minutes, Alvaro.
Okay. Okay. Well,
Thank you.
the unification of the groups was very good because the material was complementary. Really we have a very big course now. And the other thing is that we decided with Nati to include a specific notebook about classic constraints. Not to only explain the algorithm and showing how the circuits change with changing the constraints and different kinds of constraints. So it was very good. The new notebooks of this week, well, the unification and rearrangement of the notebooks from the two groups, and some improvements in the introductory notebooks. We also include the Simon's algorithm with some classic code developed especially for this. The first edition of classic constraints, a phase oracle and phase kickback notebooks that will show it Richie, and some updates to Grover and Deutsch and the structure, and two new videos about solutions, about exercises. And I can show the course. The course now have 32 notebooks. 32 notebooks, okay? These are the introductories. This is a new notebook about classic constraints with all the sets constraints and how to change, how to select the best constraints and showing the auxiliaries that appears when you change the constraints, also with changing constraints. Rishi will show you. I don't have here the last version because it's 1 hour ago. So Rishi will show you now the new new
Alvaro, I'm not sure it's
new
Abu, can you hear me? Or it's
I can hear you. I think it's from Alvaro's side. Maybe Rishi, you can.
Yeah,
You
yeah,
can
sure.
just
I will continue. I think there is some net issue from his side.
This will stop other sharing.
Can I please share my screen?
Not yet.
My sharing my screen.
Alvaro, maybe you can stop.
Yes. Okay.
Yes, thanks. Your sound just little pleased, I guess.
Okay. Yeah. So, is my screen visible?
Yes.
Okay. In this last 2 weeks, we also added a notebook on phase kickback and phase oracle. So there we explained what is phase kickback effect with its mathematical proof and how to implement phase kickback circuit using classic we use keyboard language. And then we showed how to what is phase oracle and how it's related to phase kickback and how to implement it using arithmetic oracle function of classic. And at the end, we have tasks related to the notebook. And we have also made video for this. So in this video, we had covered all the content of notebook and the solution of the tasks. So for the tasks, we are not making separate notebook. That's covered here. And also worked on Deutsch and Deutsch-Jozsa algorithm. So for that, explained what are constant and balance function, and then Deutsch algorithm with mathematical verification and yes, classic SDK implementation. Similarly, for Deutsch-Jozsa algorithm with classic implementation. And also tasks are added for this one also. Video is still pending, which we are expected to complete by this week. And also videos with last time we made notebook for oracles. This time we have video for oracle also with the tasks that we have. Solution of the tasks are covered in the video. So yeah, and right now total we have 4 videos and 1 for Global. So 6. I think some videos are still pending, which we will complete before final demo. Yeah, that's it. Alvaro, anything else? Would you cover Simon?
I mean, Alvaro, anything else you will add, or it's you are
I
done?
think that's all. No, it's okay. It's okay.
No, I mean,
Okay.
for the project also you are done, or still there are some work?
For project, we had not yet started.
I didn't get. You
So,
are done?
no, we are not adding project right now. We decided to add algorithms only.
Algorithms you will add. Okay.
Yeah.
And how much time do you need for this?
I think 1 or 2 weeks.
1 or 2 weeks.
Yeah.
I mean, what we did is already enough, but still, if you have some plans, just complete it. Also, in parallel, maybe you can start writing these 4 pages.
Okay. Pages.
Yeah,
Yeah.
overall,
I think.
it's very good
Yes,
project. Yeah.
we will write a paper about this, about the methodology of development of the course, the ideas that governs the process. I think that it's very important to see that here we are using the tool to teach the algorithm, and the idea of modifying the parameters and showing the changes in the circuits is very different than using Qiskit. I think that we can show the methodology idea of teaching with this product, teaching a quantum
Maybe,
with this.
yes.
We will write some about the methodology approach for the paper. Okay.
Perhaps some blog posts might be also interesting. I don't know what Eden would think.
Okay,
Some
okay.
popular blog post also, like something extra, not like part of this course. It would be also nice. Okay, any comment from the audience or some question?
Yes, so I think it's great work. I think I didn't understand if you have more things that you need to add still, or you finished in terms of the content of the course. But if you still have some more things to do, I would focus more on the notebooks and showing them with examples and with the graphs and with the pictures, and less on the video. I think as an educational tool, I think the notebooks themselves are a bit more valuable. I think the videos can be valuable as well, but I think they might take a bit of overhead that I think in terms of the cost benefit of developing a new notebook or recording a new video. So I think developing another notebook is a bit more beneficial, but great work overall, and I think it will be useful for people to really learn with this.
Okay, thanks.
Thanks.
Okay, thank you. We can continue with 27, project 27. Oops. 27. Oh, this is not good. 27, it's Tal, Mikhail. So we should check with Tal also, because their progress, they missed one report, individual reports, several are missing. Okay, today we are fast, 32, project 32.
Yes, sir. 32.
You are theory or application? Aditya, you are
Theory part.
theory. Okay, okay.
I will share my screen.
Aditya, we have several, not several, maybe some missing individual reports.
Yeah, but like I submitted afterwards. I had some missing in the starting.
There are several minuses. Probably, if you will be successful, you will get certificate of participation. Okay, not like passing the course, but
Okay.
still you can get certificate.
Yeah, so because of my like health condition, I had missed individual reports in the starting, but I submitted afterwards.
I see that you are still doing. This is why we are not failing you. Just you can still get a certificate. Just keep continue until the end.
Yes, sir.
Okay. So you have 10 minutes. Thank you. Overall group have 10 minutes.
Yes, sir. Is my screen visible?
Yes.
Yeah.
Good morning. This is basically the progress done by Simin regarding the behavior of the root mean square error with respect to the number of recording qubits, I mean depth, and also with respect to the number of shots of experiment repetitions. In this plot, we see the behavior of the estimation error of the quantum phase estimation protocol in blue in terms of the number of recording qubits. The black line is the quantum limit 1 over n, and the gray line is the classical limit 1 over the square root of m. When plotting the error against the number of shots, the error begins to get out of the quantum limit of the quantum limit and arrives the classical one. We are currently understanding and making the analysis of these limits for us to understand if our processing has indeed any advantage over classical limit. In this reference, for example, author gave both the Heisenberg and the standard quantum limits in terms of the eigenvalues of the generator of the unitary given the phase. But the limit that should be achieved is basically the limit of the right-hand side. In this plot, in this slide, I show that Simin plotted the error against the protocol complexity that reads the number of shots times recording qubits. We can see that the data tends to get the classical limit instead of the quantum limit. However, it is worth pointing out that a deeper analysis is required for us to conclude what advantage our protocol could actually have against others. Thank you.
And after that, as stated earlier, in terms of benchmarking, we started with comparing our quantum phase estimation algorithm with the optimized version with the K-type phase estimation algorithm to show the asymptotic improvements, and furthermore the impact of incoherent noise on QPE performance to like evaluate the effect of noise and the robustness of QPE under the various noise conditions. So in terms of benchmarking, what we found out, like due to the lesser quantum advantage relative to classical algorithms, a possible objective shot could be that some classical alternative algorithms that can benefit from the quantum nature of the quantum computers will not be able to solve in the complexity of 1 over square root of n, but we can do it with QC. So perhaps like quantum chemistry problems. In the possible end, we can still benefit from this as a tool that is useful for easy development. QPE applications developed around the world are limited to building smaller QPE with small resolution, small unitary, and small input state because of limitations of not being able to create big circuit depth. This could allow them to build, meanwhile, small QPE circuits with good resolution to examine and analyze their application, chemistry, or finance, or anything that needs QPE without compromising resolution. So once quantum hardware will be good enough, they can abandon the FIT approach because of its high complexity and return to the naive approach with big register and smaller complexity. Although one could argue how this tool could help with the analysis in the QP application during this NISQ era. So for that, I worked with some benchmarking of previous attempts that was done. And I tinkered with those attempts studied earlier about the adaptive methods based on classical machine learning algorithms that can be used to enhance the precision of quantum phase estimation when noisy non-entangled qubits are used as sensors. Those attempts, they actually employed the DE and PSO algorithms to this task to identify the optimal feedback policies, which minimize the Holevo variance. I dabbled with their way of benchmarking these schemes with respect to scenarios that include like Gaussian and random telegraph fluctuations, as well as reduced Ramsey fringe visibility due to decoherence. Although this seems like a sort of workaround at the moment, we intend to better contextualize this problem to discuss the robustness against the noise in connection with real experimental setups like interferometry with like optical photons or trapped ions, superconducting qubits, or nitrogen vacancy centers. These previous works also revealed that the fact that those machine learning algorithms that they used, they do not reach also the SQL, which is consistent with the known results that the adaptive measurements cannot saturate the Kramer-Rao inequality even for optimal measurements. So although some lighter work is done, most of the foundation is complete, and we intend to finalize our work further on. We have started with our report as well, and we have finished about the abstract and have started on the introduction part. So that is our presentation. Thank you, and we welcome any inquiries.
Okay. Samin also contributed to this presentation.
Yes, all three of us did, but actually, because Seaman had to go to China, and due to their policy of firewall, she couldn't be available today.
Okay, no, it's fine. Okay, thank you. I don't have any specific question. This group, yeah, it was ending quite good.
Thank you.
If there is no comment or question from the audience. I will ask 32 application. They said they can be late, but I'm not sure if anyone here now.
I have a question. So, Aditya, can you explain maybe in, I don't know, in 1 minute again, what, let's say, so far, what did you do and what is the goal? Because I couldn't fully understood. I know what's the headline, but I couldn't understand what actually that is that you did so far.
So basically, there's this paper, if I can pull up 1 second. I will open the paper which we are basically working off of, and in that paper, 1 second, I have this somewhere. Yeah. So in maybe I can share my screen as well. So like we started our basis on this paper, and this was the dual frequency quantum phase estimation, which mitigates the spectral leakage of quantum algorithms. And what we first we found about that they were in their math problem, they were using this approximation which was unnecessary. So we Christian, which is a Mr. Christian, which is a professor, so they worked around with the maths, and they later on worked with Kramer lower bound and Fisher information on making our quantum phase estimation more optimized in that terms. But at the end, we found out furthermore that there's, as we go on about the num shots in computation, it increases our accuracy, our mean square error, and that is lower than classical limit. So we have currently a problem, how can we extend this up, the work that we are doing, to a more practical solution.
Okay, see, so if I understand correctly, you started with this paper and then you found some part of the paper that says, or you develop your own avenue of research that says that if you can have a trade-off of measuring more and then having a better accuracy or something like this?
Yes, sir. Yes. So that is what we worked with, but our main objective was making it more optimized. So
Okay.
not to use alpha windowing in the dual frequency article, and they changed the H gates in the beginning, so the final histogram will not have any leakage. In our case, we are making a curve fit with the leakage because we know which leakage to expect. So Ron sir, they just referred us to, we can use CRLB or Fisher tools in a way to measure our quality. But there were some problems in terms of complexity, and also we are working on that in terms of near-term solutions.
Okay, and what you have left to do?
So in the end, I shared about the performance of the algorithm actually, and if I can pull that up. So yeah, so 1 second. So theoretically and experimentally, from the work that Ms. Seaman had done, we can see that the resolution is probably big O notation 1 upon depth of the square root of num shots. The fact that it is not 1 upon num shots, but 1 upon square root of num shot makes it less suitable for quantum advantage relative to classical algorithms that do the same job. So possible workarounds that we are looking for, something like lights in the dark, that is reducing depth a little bit in factor of x, which gives less strict demand for the error rate and work like that. So and other than that, the thing I talked about, but some classical alternative algorithm that can benefit from the quantum nature and do that in sort of quantum chemistry or finance problems other at a lower rate, other when a better hardware is not available.
Okay, thank you.
Okay.
Okay, thank you. So we have 32 application. The presenter is here. Okay, they informed me, they said they can join after 1 hour and it takes longer, and I promised them. So I will pause now. Okay, you can share now.
Okay, just a minute. Is my screen visible?
I see myself.
Okay, just a
Good.
minute. Sorry.
Okay.
Yes. Now the PDF.
Okay, I see. And you are doing alone this presentation?
Yes. So I have been working alone in this project. The applications part. This part is something which I have been doing alone. Yes.
So the other two didn't contribute, as I understand.
Yeah, I'm not very sure.
Okay, it's fine. I mean, you are doing. You have 10 minutes.
Okay, sure. So this is the application part of quantum phase estimation. So let's recall what we did in the last presentation. So in the last presentation, we implemented option pricing using the construct finance model of classic SDK. We directly used this method and we implemented option pricing, and we saw the results, and the results matched with the theoretical expectation. So today, as I promised last time, that we'll be building a finance model, option pricing model from scratch using different functional blocks. And the results are the codes are running, but the results are not appropriate. So I need to check back the codes and see where I have gone wrong. And there have been slow progress in the past 2 weeks due to some prior work commitments, and I have conveyed this to my supervisor. So this is the quantum amplitude estimation with QPA. This is the main circuit. We have looked at this a lot of times. Uh, so this is the main methodology used to do option pricing using quantum amplitude estimation. So first you distribute your states. So I represents the prices the options can take. Pi represents the probability with which each option price is, the probability of each option price, that's I. And here there are 2 to the power n possible option prices in this state. And then you basically load the payoff function. First, you create this state phi I using this comparator circuit, which we have discussed last time. And this state, the second sum, that is the qubit with 1, is what we are interested in, because if k is the strike price and I greater than or equal to k is the part of the option price where my contract gets executed. So once I have this phi I load f of I into this phi I, and we are interested in the probability of the second state, that's 1. And in this expression, we have this expectation of the option contract, that sigma I greater than or equal to k, pi into I minus k. So this is what we are interested in. And P1 is obtained from the execution results of the quantum amplitude estimation circuit. So what I did was I looked at all the function blocks necessary to do option pricing. First you have to prepare the state, then you have to load the amplitudes, then you have to use the Grover's operator iteratively, and then you have to wire this together in a quantum circuit, and then use quantum phase estimation. So I'll just show the codes. So importing the necessary modules, this is the first step. And the second step, the state preparation block. So I prepared this this was taken directly from the classic SDK. So I just used normal probabilities uniformly distributed from 0 to 2 to the power 8 and normalized it. So if you print the probabilities, these are the probabilities. These are the values of the probabilities. That's the PI values. This can be customized to have a user input here, which I will do soon. And this is the functional block for state preparation, and this is the amplitude loading block. These are the parameters I choose. 3.14 is the strike price, and affine maps offset 0, slope 0, which means that between 0.5 to 3.14 there is no payoff because the strike price is 3.14, and from 3.14 to 5 you have a payoff. So this map basically means if we recall the function, the payoff function f of I is basically max of 0 comma I minus k. So whenever the strike price is reached, so you have this I minus k payoff, otherwise the payoff is 0. So this is the functional block for the amplitude, piecewise linear amplitude loading. And once I have this block, then so this is the theoretical expected result, which can be calculated by a simple line of code. So you basically have to get 0.54214 as the expected payoff for my inputs given here. So k is the strike price, and these are some scaled values, and this is the expectation value. So then we prepare the good state oracle, which is the part of this composite Grover function. After that, we have this reflection about the zero state. This is that S psi 0 part, which we have discussed earlier. And then we bring this together to prepare the composite Grover diffuser, the main operator, which will be iteratively run through a controlled operation. So then once we have this, so basically let's go back to the slide. So this A includes the state preparation part as well as the amplitude loading part. And Q basically is the Grover diffuser. So Grover diffuser, the Grover operator includes reflection about the good state as well as the reflection about the zero state as well as this A part. So this comes in this Grover diffuser operator. So it includes the good state oracle, it includes the amplitude loading part, it includes the state loading part. So amplitude loading and state loading is that A operator, and then it includes the zero oracle, and again it includes the state loading operator. So, and this global phase, this operator is required because we recall that the Grover diffuser operator also has a minus sign. So that's the reason we have this. So this is the Grover diffuser operator. And once we have the Grover diffuser operator, we apply a quantum phase estimation, which includes applying Grover's operator in this controlled way iteratively, and then using the inverse Fourier transform. Then doing the inverse Fourier transform, that is done by this particular code here. So phase estimation, this particular method does this. Yeah. And then you basically execute, you can synthesize this model and basically execute the results. So I have executed the results already because this particular block of code was taking a lot of time to execute. So this was the particular circuit I was getting. So I'm not able to understand why there are two blocks of phase estimation here. So this is one question I had, which I'm trying to figure out. And the results are not correct. So this is the result I'm getting, which doesn't seem to be right, because if you extract the results out, so what you get is measured amplitude or payoff is 0, and phase with maximum probability is 0. So 0 cannot be the answer. It should be around 0.54. So I'm working on this code. So maybe next time I'll try to figure out what's wrong with this code and try to rectify it. So I'm also trying to prepare a option pricing tutorial that could explain how to build a finance model from the scratch. So that should be the deliverable next week, after 2 weeks. So that's from my side.
Viraj, thanks. Basically, collective meetings for Green Project is finishing today.
Pardon, I could not hear you.
This is the last presentation for Green Project.
Okay,
indeed.
okay. So yeah, I'm just stuck with the codes and I'm not able to, because it's taking a lot of time for me to understand all the methods of Classic and all that. But I'm actively using Slack to understand
You can still work. But you don't need to submit any progress report also, because I see that they are all fine.
Okay.
You can start to work on this 4 pages paper as well from now on. If you wish, you can do more work. That's definitely fine.
Yeah, I'll continue doing this. I also want to, since till now I was just doing for one asset option contract. So I wanted to do it for multiple assets and also different payoff functions. But now it's taking a lot of time for me to understand and, do everything from scratch. So, because I know also for now, I'm kind of doing it alone.
So you will have 3-4 weeks to write these 4 pages, and then prepare your presentation. So you can still continue work, make like your paper strong. But formally, you don't need to submit any more individual reports,
Sure.
or you don't need to make any further presentation.
Sure.
So
Thank you.
thanks. I don't know, is there any question or comments from the audience?
Yes, so thank you. Can you please show again your circuit that you received?
Okay, just a minute. Is my screen still on share mode? Oh, no, right? Okay.
You should share.
Okay, sure, got it. Here.
Okay, so you're doing a state loading and then amplitude. Can you open the state loading?
Yes.
So you prepare state. Okay, so you can close it. And then you do the amplitude loading, which is what
Yes.
is the kind? What is it? Piecewise. What's the difference? You prepare state and then you do amplitude loading of what?
This one, right? This part. This part.
Okay, but so why you need to do a prepare state before then?
No, this. Okay. So you're saying that piecewise linear amplitude loading also comes with the state preparation?
If I understand correctly, the piecewise amplitude loading, you load an amplitude of a piecewise linear function. So you do some, basically the piecewise linear amplitude loading is sort of a state preparation.
Oh,
No?
okay. So what I thought was, so when you do this, so I thought the first step was you had to load this P of I, these probabilities P of I. That was the state preparation probabilities list which I prepared. Then what I thought was that piecewise linear amplitude loaded this f of I part into this state psi. I think that's wrong, right? Because piecewise linear amplitude, what it does is it includes that factor of square root of 1 minus f tilde d uh, in 0 1. So it also has that comparator part, right? So this part basically the 5 1, it has
Yeah.
this 0 and 1s, right?
Yeah.
That's what I understood from piecewise linear amplitude loading.
Okay, can you open it again? The box?
This one?
Yeah, the functional building block. Yeah,
Yeah,
one more.
here. So if I may, 1 minute.
Yeah, definitely.
So yeah, so first step, what I thought was I prepared this D, ket D. Can you see this?
Okay, yeah, perfect. Yeah, now I see. So that's perfect.
Then I do the piecewise amplitude loading to
Yeah.
convert this.
Yeah.
Okay.
No, that's great. So, and then can you show me the next building block?
Next is
Yeah,
phase estimation.
Yeah. Okay.
Okay, but I'm not understanding why is this done twice. But this is something I'm not getting because
No, it's not twice. It's not twice. So can you open it?
Okay, this one. Oh, yeah, it's ones. Yeah, it's like two boxes. I was confused.
Yeah,
Like,
it's
why?
just two boxes because you have the qubit number 6, which just goes in the middle and the phase estimation is not applied on it. So it's just the way the IDE represents the fact that it applies on the qubits, but not on the 6 qubits is just like this. So
Uh,
for example, Grover 0,
okay.
yeah. So now the phase, Grover 0 is controlled by the Q0, and then it applies the target is Q2 until Q5 and Q7 until Q9.
Mm-hmm. Okay.
So it's not applying it twice. It's just these are the operators and the qubits that it is applied on.
But I specified the phase estimation register size to be 3. So, but it's taking a lot of qubits. One here, one here, one here, and also here. A lot of more than 3, right? So, is there any
Uh,
specific here? Because if you look at my code, I just I put 2 actually because there was some it was taking more than 25 qubits when I put 3, and the simulator was not working with more than 25 qubits. So that's why I had to put 2, but still here a lot of qubits are being used. So that's
yeah, but
something I was.
so
Yeah.
so can you open the phase estimation?
Yeah.
Okay, so here you can see that you have 2 qubits that you used as the accuracy of the phase. So you have only qubit Q0 and Q1 that you used as the phase register. And then all the
Ah,
rest is the
okay.
the control unitaries. So the unitaries, it depends on the unitary that you apply on. So these are
Oh,
two different sizes of registers and
okay.
quantum
Okay.
array that you use. So you have the phase quantum register, which you
Okay.
set the size to be 2, but then you have the operation itself. So it's control
Okay.
unitary. So the unitary is applied on a different size of states.
Okay, got it, got it. Okay, I got it. Oh, okay, I just saw that. Yeah, so here only 2 are used. Yeah, you're right. Then you
Yeah,
apply this inverse security. Yeah.
yeah.
But is the Grover operator being iteratively applied? Because I don't understand from this particular figure. Is it being applied in the sense that you see in this particular circuit in this way continuously?
Can you go back to the... So the first one should apply only once.
1
So
minute. You mean this one?
yeah, and then the second control, can you open it?
Okay.
Yeah, so you see it is applied twice, as it should. So Grover 0 should be applied. So the Grover that is controlled by Q0 should be applied once, and the Grover that is controlled from Q1 should be applied
Hmm.
twice. And
Yes,
you see
correct.
that it is applied twice.
Okay. So there is nothing wrong with this implementation here.
No, it seems correct.
But yeah, but the results are way off.
Yeah, no, maybe something else is broken within the code, but the structure seems, to me
Hmm.
at least, it seems good.
Okay.
I think you might have you need to do post select maybe on
Okay.
the on qubit 6. So only if qubit 6 is 1, maybe you need to post select the numbers because the amplitude loading, it splits basically the state, right,
Hmm.
to have a superposition of some
Hmm.
quantum register and 0 and quantum register and 1, depending on the pair function.
Okay.
So
Okay.
I think you need to dive a bit more into details over there, but the
Yeah.
structure at least seems that it's implementing what you wanted it to implement.
Yeah, that's what I was thinking because this looks so, but yeah, the results are not, the this is the result I'm getting, which is not, you know,
Yeah, I
doesn't
don't know,
seem
but
to be.
maybe something else is missing. Okay,
Sure,
but
sure.
nice. And I think you should finish up a bit more, and then I think it would be nice.
Sure, sure. I'll get back to this. Yeah. Thank you.
Okay, thanks, Viraj. As I said, you can also start to your 4 pages, up to 4 pages paper, and also do maybe the last work. You still have 3, 4 weeks, and then you can also prepare your presentation.
Sure, thank you.
Is there any? I mean, it's happy that one project finished with 2 groups, so 32 is that project. That's already nice. Before closing, any question or comment?
I had a question.
Yep.
Yes, so like this was the last green project meeting. So the next one for the blue one, the green projects will have a meeting with our own mentors, and after that, like we'll get some time because in the schedule it's mentioned like some weeks are given for like pre completing the missing reports and stuff like that. So in that time, we will prepare writing our own research paper, which is around 4 pages, and then in January, the next thing is just presentation of that research paper.
So, Aditya, currently individual reports missing too much, so it's not possible to collect for several people. And but for this collective meeting, it must be 5. Only 21 is missing one. These groups of bill, and they will do next week. So regarding this, green projects are fine. Then you should start these 4 pages, up to 4 pages. There will be 2 meetings, January 3 and January 10. So we will make announcement probably next week, beginning of next week. If you still have some work, you can continue to work. Only you don't need to formally like make these presentations, etc. You can still talk with your mentor as long as your mentors are available. You should also make presentation around mid-January, and you should make like demo presentation also. We will also write about it.
Okay,
Is it
so like
correct?
one in the starting January, there will be presentation separate for green and blue, and one final presentation.
There will be probably one day for final presentation for all groups. There will be demo presentation, not to us, for your mentors.
Okay.
It will be arranged within group. Like 1 week, you will schedule some time, but you should start to work on these 4 pages. I suggest from now on. Don't wait like January, because around January 3, probably I will ask the first draft and we will give some revision maybe. And if there are still something to do, free to do it. It's not like, okay, now we don't need to, etc. As I noticed, some projects are still wants to work even. So just continue to work. Only formally it is done. You don't need to like submit issue, etc. Of course you can do, but I mean we will not create them, something like this.
So is there I had a doubt, is there a scope of, continuing, suppose some work is not completed by the given deadline and we want to do more, like we have more ideas but need more time.
So course has like its own time limit and it will finish.
Okay.
If you want to work more, you should talk with the mentors.
Okay.
Like,
Okay.
can you continue after the Q course? This is something you should do with mentors, because our course is like, okay, today's collective meeting is finished. Now I am assigning these 4 pages to you. You understand? And then I will ask final presentation, and then we will check pass, etc. And then we will distribute to the successful one their certificate. So this is finishing. The rest is up to your mentor. If your mentor is not positive, you can talk with your group. So it's definitely up to individuals here.
Sure. Thank you.
I hope, I mean, some projects, of course, continue because this is a project course, and yeah, it should continue definitely. But I don't say anything from my side. Okay, course will finish.
Okay, thank you.
Welcome. Any other question or comment? Okay, we will make a big announcement, let's say next week. We are now talking details with Eden, so you will get But you can start these 4 pages. That's definitely, you don't need to wait.